Now we want to investigate how to describe the motion of an object that is moving in two dimensions. To start, we'll start out simply. We want to describe what happens if we take a ball, for example, and kick it off of a cliff, and we're going to give it a perfectly horizontal initial velocity. So conceptually, what's happening here? What's happening is the ball is going to fly off. Let's look at a special case first, and we want to compare it to something that we already know. What we already know is this situation where we're going to take a ball and we're just going to drop it with an initial velocity of 0. Okay, so if we take a ball and we're just going to drop it, we know it's going to fall down. If we take a ball and we kick it off the cliff, we also know it's going to fall down. What's the similarity and what's the difference between these two situations? First of all, just for comparison, let's think about what would happen if I was able to turn off gravity. So what would happen to this ball if I let go? Starts out with initial velocity and there's no gravity. If there's no gravity, of course, the ball is just going to sit there. It's just going to float. And while that would be cool, we know it doesn't actually happen. What about this case? If I kick a ball with an initial velocity in that direction, what's going to happen if there's no gravity? If there's no gravity, it's just going to go and it's going to keep flying straight until, it hits a wall or something. So that's sort of my no gravity baseline. What is really going to happen to the ball? Well, of course, this ball is going to fall straight down, and we know how to calculate how far it falls, how much time it takes, what the final velocity is going to be. What's going to happen to this ball? If this ball goes, it is going to fall down. The zero gravity case isn't obviously true. It's going to fly out and it's going to fall and it's going to look something like this, right? And it's going to land over here somewhere. What's the similarity between these two? Let's calculate, for example, for this case, the ball just dropping straight down. Let's calculate how far does it fall in 1 second, 2 seconds, 3 seconds. So how far is the fall? Okay, so how would we do that? V0, VAT, delta y. Let's put our coordinate system somewhere. So my coordinate system maybe is going to be down here at the bottom, x and y. So how far does it fall? I'm looking for delta y. I know that my initial velocity is 0. I know that my acceleration is negative, because it's down, 9.8 meters per second squared. And let's say for the first one, how far does it fall in 1 second? How far does it fall in 1 second? We could say delta y equals v0t plus 1/2 at squared. So delta y is going to equal to 0 plus 1/2 times negative 9.8 meters per second squared times 1 second squared. So it's going to end up being delta y is negative 4.9 meters. Okay? So after 1 second it falls. This is my 1 second case. After 1 second it falls 4.9 meters. What about after 2 seconds? After 2 seconds, does it go 8 meters, 10 meters? What is it going to be? So we could do the same thing. Delta y equals v0t plus 1/2 at squared. Is it going to equal to 0 plus 1/2 times negative 9.8 meters per second squared times 2 seconds squared? And so 4.9 times 4 is going to be 19.6. So in this case, delta y is going to equal to negative 19.6 meters. So in 2 seconds, it falls 19.6 meters. And similarly, what happens after 3 seconds? You can see what happens. We're doing the same thing. We end up with delta y equals negative 4.9 meters per second squared times 3 seconds squared, or delta y is equal to negative 44.1 meters. Right? So we can sort of see what happens. What happens in this case is the ball, I'll use a different color, after 1 second, right, the ball falls 4.9 meters. At the second, it's 19.6 meters. After the third second, it's maybe way down here at 44 meters. So it falls faster and faster and faster because it's speeding up. What's similar about this case? What's similar about this case is that after 1 second, the ball has fallen 4.9 meters. After 2 seconds, the ball has fallen 19.6 meters. After 3 seconds, the ball has fallen 44.1 meters. So the distance that the ball falls, right, in this case, that distance or that distance or that distance in 1, 2, or 3 seconds is the same regardless, right? The vertical fall is affected by gravity. It's affected by the 9.8 meters per second squared. So the vertical part of these two problems is identical. What the difference is that the difference is this one also has a horizontal component. This ball has no horizontal component, right? It's only falling straight down. It's not moving in the x direction. It's not moving left or right. This one is moving left or right, but it turns out that the left and right, the x component, is unrelated to the vertical component. So we'll notice after 1 second, the ball has traveled this distance. After 2 seconds, it's traveled that distance again. After 3 seconds, it's traveled that distance again. So it's traveling constant velocity in the horizontal direction. There is no acceleration. So there is 0 horizontal acceleration, and there is negative 9.8 meters per second squared vertical acceleration, right? So the difference is, if there's 0 horizontal acceleration in both of these cases, it can't speed up or slow down in the horizontal direction. So we now see that if we take what we know how to do the vertical case, we can take this ball that's thrown in 2 directions, and we can actually just break it up into components. All right? We can say, let's break it up into a horizontal component, where we know the acceleration, and a vertical component. Functionally, the way we're going to do that is we're going to have our variables v0, va, t, delta x, and we're going to have 2 different columns of variables, one for the horizontal and one for the vertical. So in this case, in the horizontal direction, what's happening? Well, we need to have some numbers here. So let's say that I give it an initial velocity of 20 meters per second, and let's make this cliff, I don't know, 60 meters high. Okay, and what questions would I ask for this? I might ask, what's the total time in the air? I might ask, what is the distance? Like, how far? What's this distance? Where does the ball land? That might be an interesting question. Okay, so let's plug in what we know and make sure that we're clear on that. What do I know? Do I know the horizontal velocity? I know that the horizontal velocity is 20 meters per second. I know the acceleration in the horizontal direction is 0, so I get 0 acceleration. What else do I know horizontally? I don't know my do I know my horizontal final velocity? I do, because if it's 0 acceleration, the velocity works horizontally, or final and initial doesn't change, right? 0 acceleration means 0 change in velocity. I don't know how much time it takes to get to the bottom, and I don't know how far it's gone. That's actually what I'm looking for. What's going on in the y direction? Do I know the initial velocity in the y direction? Yes, it's not moving in the y direction initially. It's only going straight across, so I have 0 meters per second initial velocity. I know that in the y direction my acceleration is 9.8 meters per second squared down, so the down is the negative. And I know in the y direction that my total distance traveled is 60 meters. That's the displacement. And it's down, so I lost my 60 meters. In this case, I have 3 things in both columns. So what the common feature between these is that the time that it takes to get to the bottom is the same horizontally and vertically. The ball doesn't split in half and go down faster than it goes sideways. It's one ball, so the time that it takes to impact has to be the same. So now we can just use our kinematic equations. I know in the y direction v0a and delta x, so I can say delta x equals v0t plus 1/2 at squared. So I know that negative 60 is equal to v0t is 0 plus 1/2 times negative 9.8 meters per second squared times t squared, which I don't know. So negative 60 is equal to negative 4.9 t squared. So t squared is equal to, go plug that into my calculator, 60 divided by 4.9. T squared is equal to 12.24, and then square root. So my time is equal to 3.5 seconds. Okay? So I can go ahead and plug that in. I know that the time that it takes to hit the ground is 3.5 seconds. Because it's the same, I also know that the time to hit the ground in the horizontal direction is 3.5 seconds. And now I know everything in this column. I can find the delta x. So this one here is the vertical problem, right, or the y problem. Let's do the horizontal problem, or the x problem. In that case, delta x is equal to v0t plus 1/2 at squared. So delta x is equal to 20 meters per second times time of 3.5 seconds plus 1/2 times a, which is 0, so all of that goes away. So I end up with equals 70 meters, right? So delta x is equal to 70 meters, and you notice that just by filling in the chart, I have figured out my total time in the air. Total time in the air is 3.5 seconds. Where does the ball land? 70 meters. 3.5 seconds, 70 meters. 70 meters from where? From the edge of the cliff. This is what we were looking for, is 70 meters. Okay? So that's the general theory. We know that there's a connection between the horizontal and vertical, and that connection is the time. But we treat them independently because they have different accelerations.